Hello everyone, my name is Maya. I'm a postdoc in the Department of Earth System Science at Stanford University, and I am very happy to virtually present my talk, Biogeochemical Variability Controls Heavy Metal Mobility within Alluvial Aquifers. So we chose to focus on zinc. At low levels, zinc is a micronutrient for many microorganisms, plants, animals, and even humans. But due to geogenic and anthropogenic processes, we know that heavy metals can exceed their nutrient levels and reach toxic levels to living organisms, where the major concern is toxicity to plants, reduced crop yields, and of course potential exposure to animals and humans through polluted groundwaters. But in both cases, the origin of the metals lies really in the behaviour of the heavy metal in the soil system, which is why we are specifically interested in heavy metal mobility in a model aquifer. This is a typical aquifer. Thanks to the layer of water permeable materials confined by a layer of impermeable materials, water accumulates and stores our beloved groundwater. Now, in our study, we imitated an alluvial aquifer where the permeable layer is mainly composed of sand and gravel that was once thought to be relatively homogeneous. Indeed, on a macro scale, it may seem homogeneous, but if you look closer, you can see that fine-grained lenses are in fact embedded in the sand. These lenses are typically rich in reactive materials, such as clay organic matter and reduced iron and sulfur. Owing to their composition, they form different redox environments within the aquifer that may have immense influence on heavy metal behaviour and the resulting groundwater quality. This is particularly important as aquifers are a major source of drinking water worldwide. So we hypothesized that the fine-grained lenses would have appreciable influences on zinc behaviour and on the resulting groundwater quality. Our primary goal was to assess how these fine-grained lenses influence the mobility of zinc. So we modelled an alluvial aquifer by packing columns with sand and two lenses of the fine-grained sediments that were collected from a floodplain in Riverton, Wyoming. To account for the influence of the lenses, we added pore water samplers throughout the columns at specific locations that allow us to fully monitor the activity in the column. This was all done in parallel to control columns containing just the sand, where there are no B and D ports. On the left, you can see how it looks in the process of packing the columns. We then passed artificial aerated groundwater that simulates the composition at Riverton, which has high sulfate concentrations, and at week 3 of the experiment introduced zinc. We worked with relatively high concentrations of zinc so we could thoroughly examine its behaviour and speciation. We'll quickly sum up the experimental details. The duration of the experiment was 11 weeks. There was a total of 6 columns, 3 columns containing the 2 lenses and 3 control columns containing only sand. The groundwater was prepared freshly every week. The columns were wrapped in aluminum foil to keep as much in the dark as possible. And we sampled all ports once a week and measured concentrations of heavy metals, nutrients, ferrous ions, sulphide, organic carbon, and inorganic nitrogen species. Let's start with getting a sense of the aqueous phase during the first few weeks to understand our system. Looking at organic carbon, you can see in the lens ports B and D that a large amount of organic carbon is being flushed out in the first 2 weeks, which is also apparent in the sand that follows both lenses. Now, because these levels weren't as high in the effluent water, it suggests that at least some of the organic matter is being transferred from the lenses into the sand. Moving on to ferrous iron and observing the trend throughout the experiment, ferrous iron levels were higher in ports following the lenses, especially C and E, meaning the lenses act as a source of reduced iron and manage to distribute it into the sand by maintaining reducing conditions or reducing iron in the sand itself. Sulphide was only detected in the presence of the lenses, within the lenses themselves, and a bit in the succeeding sand. We see stable levels in the first 2 weeks, but at week 3 the sulphide drops and is undetectable at week 4 and onward. Now, if we recall, zinc was introduced into the groundwater at week 3, so it appears that the metal is interacting with the sulphide and producing sulphide minerals that are removing any dissolved sulphide from the aqueous phase. If we now look at the zinc data, we see how the zinc is gradually making its way through the columns. Most importantly, there is nearly no dissolved zinc in the lenses, suggesting the zinc is either immediately captured within the lenses or that it completely bypasses them. Also, the fact that zinc levels were lower than in the incoming groundwater shows that the zinc is being retained just by the sand. We see the levels in the sand levelling off between the ports in the sand at week 8, but then decreasing further at week 11, suggesting that during the first few weeks one mechanism dominates, perhaps adsorption or a fast precipitating mineral phase, and after all sites are saturated, a different mechanism becomes more dominant, likely precipitation of a different mineral phase. After the experiment was done, we performed solid phase analysis for the elemental composition and conducted chemical extractions. Now looking at the solid phase analysis, the pattern is quite different than what we observed in the aqueous phase, and here higher amounts of zinc are found in the lenses, demonstrating that zinc is being removed from the dissolved phase and captured within the lenses. And if we add in the distribution of the chemical extractions, we can see in grey that more zinc was left in the residual phase in the lenses compared to the sand, implying that there is a difference in the chemical speciation of zinc between the sand and the lenses. We are now working on X-ray absorption spectroscopy data to unravel the chemical speciation of zinc, so stay tuned for future results. To conclude, fine-grained lenses embedded in an alluvial aquifer system have profound influences on the biogeochemistry and resulting speciation of heavy metals. This provides important information on the mobility and availability of heavy metals in groundwater systems. I would like to thank the Fendorf team at Stanford and the SFA group from SSRL and all of you for listening in. Please join our Q&A session, and I'm happy to take any questions at that time or via email, of course, and hopefully we can meet next year in France.